I mean, it's just crazy what you can do today. I mean, our team is very small. Our company does not have that many people, but like, if you lean on good primitives like AWS and, their network load balancers and their object storage and some of their data stores, I mean, you can build mature, battle-tested infrastructure that would have required, hundreds of people to build just 10 years ago.
What's your billing model? How will people use WarpStream? Is it fully hosted service? Is it sort of run your own? Like, what's it look like there?
WarpStream is designed with a data plane, control plane split. And so the idea with the BYOC product is the data plane runs in your cloud account and the control plane runs in ours. So there's essentially no networking fees between the two cloud accounts except for metadata, which is super small, on the order of tens to hundreds of kilobytes per second. And also you get all these nice privacy and security benefits because the data literally, doesn't leave your cloud account. We call that BYOC. We're still kind of going back and forth on the pricing for that. I think most likely what it's going to end up being is just usage-based pricing on 2 dimensions.
Would it make sense for a cloud provider to offer a FoundationDB primitive, like a managed version, or does it sort of not work because it's like, I don't know, so low level or something like that?
I would love if someone did. That would be cool. But it's definitely a big engineering challenge. And I imagine anybody that gets close to that, they would probably want to start from scratch and just build a new system that had the same semantics instead of using FoundationDB directly.
Hey folks, this is Alex Debris. This is one of my favorite episodes. I just spoke with the founders of WarpStream Labs, Richie, Artoul, Ryan Worl. They're super smart guys. I love what they're doing. Basically what they're doing is, taking Kafka, an existing technology, and saying, how could you make it better if you change sort of one constraint or use a different piece of technology there? I think that's just a super fascinating space to play in. So we talked about, their approach, what are the implications and takeaways of it, lots of practical stuff if you're using them or thinking about using them, but also just like a lot of, foundational conceptual stuff around build versus buy when you're building a data storage system, or FoundationDB, or we even talked about like cross AZ network costs in AWS and, is that a racket or not? So I love this episode. I thought it was a lot of fun. Check it out. As always, if you have any comments on the show or anything, reach out to me, reach out to Sean Faulkner, and let us know what you'd like to see, who you'd like to see, anything like that. And with that, let's get to the show. Richie, Ryan, welcome to the show.
Thanks for having us, man.
Thanks.
Yeah, absolutely. So you two are the co-founders of WarpStream Labs. Super excited to talk about this because I think it's really fascinating, and some of the writing and stuff you've done around Kafka and what you're doing at WarpStream is very cool. For those of the audience that doesn't know you, can you give maybe just a little bit of your background, maybe starting with Richie?
Yeah, sure. I'm Richie. I'm one of the co-founders of WarpStream. Before I founded WarpStream with Ryan, we both worked together at Datadog on a basically a columnar database for observability data called Husky. And there's some good blog posts about that out there that you can go read.
Yeah, my story is pretty similar to Richie. For the last 5 years-ish, we've been working together either at Datadog or on WarpStream. We're really excited to talk to you.
Awesome. Yeah, Husky's a really cool thing. I'll share some links in the show notes, like blog posts, also a really good video about Husky and how it works. So cool stuff there. But let's move on and talk about WarpStream, which I think is a really cool, sort of interesting entrant into like the Kafka space. So maybe just give me like the quick rundown of what WarpStream is.
WarpStream is a Kafka protocol compatible data streaming system that stores data directly in object storage, and object storage is the only storage for data in WarpStream. The main difference between WarpStream and a system like open source Apache Kafka is that because the primary storage location for the data is in S3, there's no like tiered storage or worrying about your brokers running out of disk or anything like that. You just get to use the infinitely scalable and extremely reliable storage that is provided by all the hyperscaler cloud providers today.
Awesome. I love it. So like, I think you're in this category that I really like right now, where it's like, hey, there's an existing tech or protocol or something like that, and something has changed, which might be like maybe some piece of technology has changed and really improved and changed how we build things, or maybe like a constraint or requirement is not true for like a large segment of the customer base, and that can really change how we architect things and design things. And so like as I look at WarpStream, it's sort of like, Kafka provides all these things, including like, end-to-end latency on events of maybe sub 100 milliseconds, sub 200 milliseconds. And it turns out that like a lot of people don't need quite that low of latency. Like that's nice, it's cool and all that stuff. But if you like, expand that range by like an order of magnitude, most people are still fine. And that just opens up like a lot of capabilities, right? Like including using object storage. Is that like the right way to think about WarpStream?
Yeah, I think that's a really good way to think about it. The numbers we usually tell people is on the produce side is between 400 to 600 milliseconds at the P99. So that's between your client deciding to send a batch of data and having it acknowledged as fully durable. And there's some knobs you can tune there if you're willing to spend more money. And then roughly 2 seconds, second and a half to 2 seconds, depending on how you tune it, P99 from the consumer decided to write some data and the producer decided to write some data and the consumer received it. And it turns out for like a huge majority of use cases, that's totally fine. That's still very real time. And so that's part of the observation. The other thing I've kind of noticed too is that we'll have a lot of people come talk to us and they're like, I have this one use case. It's like super latency critical, so I can't use you there. But I have this other use case, it's my telemetry data, my log data, whatever. And that's not so latency sensitive. And so I could maybe use you there. And then we talk to them a little bit more. And when they realize that the end-to-end latency is only 2 seconds, they're like, that other latency sensitive use case, I like that it's low latency, but am I willing to pay 10 times more for it to be low latency? They tend to. So even a lot of the low latency kind of use cases, we've found that people are willing to be more flexible once they see the benefits of not having to manage brokers and the not paying for interzone networking and all of that type of stuff. But yeah, that was definitely one of the core observations we had, and a lot of that came out of I've been working in the observability space for like 8 years, and so we're kind of coming at the data and Kafka space from I think a different background and a different angle. And I think that's helped a little bit too.
And now with the announcement of S3 Express OneZone, we also have the option to run on even lower latency storage. So it's I think regardless of what the latency characteristics are of WarpStream today on S3 standard, we'll be making a new release at some point early next year that supports S3 Express OneZone that will make those latency characteristics look a lot more like a traditional open source Kafka cluster or one of the other providers.
And I think that'll get really interesting too, because you'll get a knob basically that's like, I care about latency and I'm willing to pay more money, or I don't, but you won't have to change the architecture. And I think that's a really neat thing, basically, to not have to have completely two different solutions to hit different parts of the price performance curve.
Yeah, it's just like a config flag, right? Right to this bucket or right to that bucket or something like that. Yeah, amazing. Yeah, I think you all have done. You wrote a blog post right after Express OneZone came out, and I think it was like the most astute one. I think a lot of people sort of misunderstood what OneZone was for and who's going to be using it, types of thing. And I think it's more for infrastructure providers, data infrastructure providers like yourself using it for interesting things. And I thought that y'all noticing that it just makes it so much easier to have like, hey, higher latency but lower cost system, or a lower latency and higher cost system very easily without having to have like a whole different storage subsystem. Basically, I think that was really interesting and astute. I want to talk a little bit more about just like how WarpStream, like what's happening with WarpStream. Because when I first heard no local disk, it's all object storage, I'm like how are they just writing every single segment to S3? Like you're just gonna have tons of files all over the place. It's gonna be super slow. So just, without getting like too deep into it, like what's happening on one of these WarpStream broker agent type things when some request comes in? How do you do that without any local disk and just going straight to object storage?
Yeah, so the basic idea is that your Kafka client has settings that allow it to batch records that are being sent for all the topic partitions that you're writing to. So that's step one. Is your broker or your producer client library already does a little bit of batching for you. When a batch of data is sent from the client to one of the agents, as we call them, which is like a stateless broker, basically, the agent also buffers records in memory from batches that were sent from multiple producer clients. And those records are batched together, and every 250 milliseconds by default, we write a new file to object storage. Once the file has been written to object storage, we send the metadata for that file back to our control plane, and the control plane does the ordering to decide which records are assigned which offsets in the Kafka, semantics of ordered data per partition, offsets are monotonically increasing, all that stuff. So we fan in records and batches of data sent from multiple clients on the agent, and then the agent writes files to object storage, and we assign the offsets inside the metadata store. Once that happens, you're correct that there will be a lot of files in S3 if that was all we did. So we also perform background compaction, where the agent will download the small files, merge them into bigger files, and replace them in the control plane. And that happens in the background. It's not in the critical path of the requests, but it's performed by the agents. On the consume side, the small files creates its own problem. We wrote a blog post about our distributed file cache, but the basic idea is that the agents form a consistent hash ring, more or less, within each availability zone. So your client can request to read data for a specific topic partition, and that request is routed by a round robin to some agent. And then the agent will use the distributed file cache to read from all of those tiny little files. Ideally, just, it's read once from S3, pulled into the distributed cache, and then all of the reads for that topic partition and all of the other topic partitions in that same file, because they're all merged together into, there's no relationship between the files and which topic partitions they contain. That's all handled by the mapping is all handled by the metadata store. So yeah, that's basically the full end-to-end flow. It's, we fan in records with the brokers, we do background compaction, and then on the read side, we have a distributed cache to make sure the gets are efficient.
And I think the architecture he's describing too, especially the combining multiple topic partitions into one file, so each agent is basically making one file every 250 milliseconds. I think a lot of the disappointment around S3 Express one zone was like, a lot of people wanted to be like EBS+++, and it's not what it is. It's like you still, I think there's a lot of people kind of still stuck in the category of lift and shifting existing systems into the cloud and then trying to like bolt S3 at the end of a traditional data storage system. And if that's what you're doing, S3 Express won't help you at all. But if you've redesigned the entire storage engine from the ground up around object storage, then the S3 Express one zone pricing actually makes a lot of sense. And because it's like you've already, if you just try and like flush the disk every couple of milliseconds like you do with EBS with S3 Express one zone, it's still gonna be extremely expensive and it won't work. But if you have a storage system like WarpStreams where it's like, okay, it's already, everything has been designed around minimizing the number of API operations that you're performing, and you can just pay more money to make those API requests fast, you end up with something that's actually useful. So,
very cool. And just so I understand it, so we talked about like loosening sort of the latency requirements on that stuff, and as I see it, there are like two main benefits of this. Number one is just cost, right? You're not doing any inter-AZ cost, which like Kafka is just sort of notorious for paying, just like the sort of communication across brokers for replication just being prohibitively expensive for these large workloads. So cost number one, but then just also like ease of operation, right? Because you don't have these more stateful brokers, they're stateless. So around that, like every single agent can handle every partition of every topic in your cluster. And then so it is, is throughput just like essentially a function of like how many of these agents I'm running, and I can just scale them up and down like with my traffic pretty easily?
Yeah, that's exactly how one of our customers runs it in production today. They deploy the agents in Kubernetes and use the built-in auto-scaling functionality to add and remove agents just based on CPU usage.
Wow. How quickly can I spin up a new node and have it start actually taking traffic from producers or consumers?
It's basically as fast as you can launch a Docker container. There's some nuance in the Kafka protocol, which is that there's like a service discovery mechanism in the Kafka protocol itself. So basically, your clients are not constantly, it depends on how you tune them, but like querying Kafka, through the protocol. In this case, it's WarpStream, asking what brokers exist and what partitions are assigned to each of those brokers. And I think this is kind of one of the interesting things about WarpStream too, is that so in a traditional Kafka cluster, when you hit that metadata endpoint, what it's going to tell you is, okay, there's 1,000 partitions and roughly, let's say you have 6 brokers. 1/6 of those partitions, the leader for that partition is this broker, right? When you query for metadata in a WarpStream cluster, let's say you have 6 agents, it'll tell you there's 6 agents, but it'll pick one of them, and it'll be like, that agent is the leader for all of these partitions. And so all the traffic from one client will be routed essentially to a single agent. And when we make that selection, the control plane does that, and we can do essentially round robin load balancing. And so you end up almost with like a kind of like HTTP round robin load balancing strategy, but within the Kafka protocol. Now those connections are sticky, right? Because of the way the Kafka protocol works. And so the way that you can control how fast you can react to changes in the kind of quote unquote cluster topology is just tuning your client to how often it requests a new view of the cluster. So you can tune that as low as like a couple seconds. Most clients default to like 5 minutes because most clusters are fairly static. But you can tune that really low, and then they'll react really quickly.
Wow. Yeah, that's amazing. I do want to talk about like the Kafka protocol stuff, because I think there's some interesting stuff there. But just like on the scaling up and down type stuff, like I'm not that familiar with how people are running super high scale Kafka clusters right now. But are those scaling up and down frequently, or are those like pretty static? Like you're provisioning for peak and you're paying for it, and you like scale it up one time a year or something like that if you need to.
The number of organizations with the like Kafka maturity and tooling that they can even scale a Kafka cluster down is like very small. Like most companies have figured out how to scale up a Kafka cluster, do basic node replacements. I meet a huge number of companies who just don't know how to do upgrades. I mean, it's not their fault too. It's just like really hard. And then when you do an upgrade, usually they want to like replace the broker, and there's a bunch of data being transferred. And a lot of these companies have like, because it's so annoying to run a traditional open source Kafka cluster, they just have one, right? Because they're like, I can't deal with more than one. And so it just keeps getting bigger and bigger and bigger. And the bigger it gets, the more scary it gets to touch it. So I would say the number of people who are actively downscaling their Kafka clusters is very, very, very small. And so the fact that we can do the automatic scaling with WarpStream is a really nice benefit. I mean, you can spend years with people, a team building tooling, and still get to an okay place, but it takes a long time.
That's amazing. Okay, so talking about the Kafka protocol one, because I thought that was a really interesting post you had, like where you had to, respond with this metadata request, but tune it for the different topology of just like how your thing works. So as I understand it, like in that response changing, there are 2 big benefits you were looking for. Number one is reducing cross AZ traffic again, right? You want to have your clients connect to agents in the same AZ. So you're not paying that cross AZ, but then also directing all the writes from a producer to a single agent, rather than being like, hey, all the partitions, here's their leaders. And now if I have 128, partitions, it's making requests to all those different brokers as part of that. Like that second one's really interesting. How much does that make the producer that much more efficient? Like, is that making a meaningful difference on the producer, or is that pretty negligible anyway that they had to make all those separate requests?
Yeah, the big benefit there is you actually get, well, it's tricky because of how the Kafka protocol works under the hood, because it's separate batches for each partition still, right?
Yeah, so you don't get a compression benefit. The compression happens at the unit of a batch that is destined for an individual topic partition. But the reason why it's helpful for us is that it makes sure that your client is not exposed to the outlier latency of every node. It's only exposed to the latency of one node at a time. So ideally, your the upper percentiles of the latency will look a little bit better. It's
a lot better in practice for large clusters.
It depends on your partitioning strategy. Like if you're using a partitioning strategy that writes to all of the brokers all of the time because you're using like key-based routing, then it really is bad if you have to write to all the brokers. If you use one of the other partitioning strategies that just writes to a few at a time, it's a bit better. But in general, that's why we did it. Yeah.
You also get some additional benefits too, though, because like a common scaling limitation that people run into with really large Kafka clusters, and it doesn't even have to be like a high throughput Kafka cluster. It's just a cluster that has a lot of clients. Is that if you have a lot of clients that are writing and reading to a lot of partitions, you end up with this huge mesh of connections. Because if you have like 1,000 connections, if you have like 1,000 clients and like 50 brokers, it's M times N, and you end up with this huge number of, and that just starts. There's a lot of time spent in the kernel for TCP keep alives, and you have to maintain buffers for each connection on both sides and all that kind of stuff. With the approach we take with WarpStream, or at least the default mode, is you essentially end up with like each client results in roughly one additional connection to the cluster. And so it scales a lot more like a Nginx proxy or something than it does like a traditional Kafka cluster. You can actually, we do support a mode if you like really know what you're doing, where you can make the topology look like traditional Kafka, where we assign partitions kind of evenly to each of the agents. And that can be useful in scenarios where you have producers that tend to not write to all the partitions. For example, if you're building like a sharded database and you're using WarpStream as essentially as the communication layer between clients and consumers and stuff, then what you can do is, if you do it that way, then you can kind of get the benefits of improved data locality by having all the data for a given partition being buffered in a single agent without being exposed to kind of the outlier latency of all the agents. So you can like essentially flip a switch and change the topology, and you can actually do it per client, which is the really weird thing. Is like you can have one client that has a view of the cluster where one agent is the leader for all partitions, and you can have another client that has a view of the cluster where the partitions are evenly distributed, and that doesn't cause any correctness problems. And then you can even take it another layer further, which we haven't built this yet, but we're planning on adding it soon, is this idea of like server-side partitioning, where you can have a producer that sees a topic as only having one partition, and which partition records go into is decided by the agent at like commit time, basically. But the consumers can see all of the partitions, and so you get essentially perfectly optimal
batching and compression
on the right side.
Yeah.
But the consumers still get all the benefits of concurrency of having many partitions. So and you can do that within like each client can make that decision for themselves if they want.
Very cool. Okay, and yeah, as I was reading that protocol article, it's like it makes sense on why you want to fit with the Kafka protocol. It makes it super easy for migrations for existing people, but it's a lot of back-end work. And I was like wondering, would there be any benefit on the producer or the consumer side if you had a client that knew about your topology or just knew about WarpStream and how it worked? Like, other than getting rid of a bunch of server-side code, would that actually help? And it sounds like it would, because it could know just that, hey, send it all in one batch, compress it all together, don't split it up into different topics and partitions and things like that, even though they're all going to the same broker. Like, you get some benefits of that. So have you thought about, having your own client for that sort, I guess, or would this server-side partitioning do that for you?
I think it would mostly do that for you, to use the server-side partitioning feature that we're planning on building soon. Overall, we'll probably just add an HTTP interface because it's easy. But yeah, right now we're going to stick with the Kafka protocol just because so many different things integrate with it.
It's also just like a lot of work to build. You can spend a lot of time on building a good protocol and getting good bindings in every language and convincing people to rewrite their applications and stuff. And I think we found enough. I think we probably have more. We've probably run into more issues with like the actual implementations of the Kafka clients than we do with the protocol itself, if that makes sense. And so I could see us spending a lot more time and energy investing in improving existing clients, but I think we can get pretty far with the existing protocol.
Yeah. And on that note, just for others, like go read that Hacking the Protocol post. I thought that was interesting at the end on like some clients, how they treat host names like case sensitive, but DNS does not, and just like how you use that to your benefit to like set it out. I thought that was super cool.
Yeah, it was not fun to debug, but it was fun to debug.
It's amazing how you found that and then like figured out how to use it to your advantage. I thought that was just really cool. One thing I want to ask too is just like, so how does WarpStream setup change like advice around either like how many topics I should have or how many partitions I should have? Like, should I have fewer partitions and basically just like saturate a node for a partition, or like how should I think about number of partitions for a topic? Does that change as compared to regular Kafka?
I think the main difference probably with traditional Kafka is that there's effectively no write throughput limit on a given partition. Like you can make a WarpStream topic with a single partition and like write a gigabyte per second into it. The problem you'll have is then like trying to parallelize consuming that partition on the other side. Like you're just never going to have a consumer that can consume a gigabyte per second unless it's doing like literally nothing. And so I think the way we usually explain it to people is just like the number of partitions you need if you're using consumer groups and not managing, because you can write a consumer that like looks at all the offsets that are available in a single partition and chunks it up and divides it out to a bunch of workers. But if you're just using kind of a standard consumer group where, you know, you get assigned a partition and you read it in order, partition selection is essentially a function of like how fast are your consumers and how many consumers do you eventually want to be able to scale up to. The system is still more efficient if you have less partitions because you get better batching. There's less RPCs in the system. There's less syscalls and IO and that sort of thing. But really, I think it's more a function of how much how fast your consumers how fast can your consumers consume. We've done some discussion too about having like whatever it's. Different people call this different things, but like topics where you don't have to think about how many partitions there are. There's a couple of different approaches you can have to that. Like Kinesis can split partitions, for example. So you can imagine kind of doing that automatically for people, because then you get data with the same key always goes to the same partition. Or if you have people who don't care about the number of partition, like they don't care necessarily about like which data goes to which partition, they just care about parallelism. You can do something like you can automatically modify the number of partitions based on the observed throughput and increase it and decrease it. So there's a number of, I think there's still a lot of room for innovation there, but we haven't gotten into it yet.
But the important thing is that the traditional concerns of I need to make enough partitions that like aren't too many for my brokers to handle, but also I have enough to parallelize my consumer application, or like if my retention is super long, I have to have a lot of partitions so that like the unit of movement of data between brokers when a broker fails isn't too big that overwhelms the network. Those concerns are not as important anymore. It's mostly just about making sure that your consumer application can keep up.
Yeah. What about number of topics per cluster now? Because I think, like you were saying, like a lot of people just end up with this giant Kafka cluster with all these brokers because it just like maintenance wise that ends up easier. But now if it's easier to sort of scale up and down my cluster of agents here, does it make sense to have fewer topics per agent and just like have a new cluster? Like if I have a new topic, just create a new cluster and scale that independently.
Yeah. So we're pretty big fans of like cellular architectures. I think that's like a really good strategy for people. So we've been trying to think about how we can like make this easier for people and encourage people to do it more. But like, if you're like a large company, it's so much nicer to have like, let's say you're a company with a couple hundred, or maybe more like a couple thousand people. Your overall Kafka cluster traffic is 1 to 2 gigabytes per second. I mean, that's not a crazy huge cluster, but it's really nice to be able to say, in my opinion, like, okay, there's some data science topics over here, and there's some like extremely business critical topics over here, and this is the cluster that no one cares about, and we just dump our logs into it, and we want it to be as cost effective as possible, right? Because what I see happen a lot is like when these clusters get too big and there's only one of them, and you have a mixture of very important workloads and low value workloads in the same cluster, eventually like the people responsible for the cluster start saying like, no, you can't use it, you can't put this in there, give me exact numbers on your throughput, and predict the future, and all these kinds of, you end up with like a kind of like a lot of, and not because they want to stop you from doing stuff, they're just like, if this falls over, the whole business is done. And so I definitely think that like limiting your blast radius to specific size logical clusters so you can be a lot more comfortable basically making changes, doing upgrades, experimenting, right? I think that's definitely something we'd like to help people with. And I do think it is a lot easier once it's like literally like, okay, they can all share a massive S3 bucket, but all the compute is fully isolated and they can be upgraded independently, and you can do rolling restarts and all that kind of stuff. And you can run them on different hardware. And even within a cluster, what you can do with WarpStream is you can split the roles. So what you can do with a WarpStream cluster, like by default, all the nodes run the same role. But if you're a slightly more advanced user, what you can do is be like, okay, these agents handle writes, and these agents handle reads, and these other agents handle background jobs. Then you can split that onto different hardware groups. You can upgrade them independently. You can scale them independently. So you can even get isolation within a cluster for different activities, basically.
Like you could deploy 2 different sets of agents for reads and give the data science team for their crazy Spark job that has to read the whole world every hour. You could give them their own dedicated deployment of reading agents, and you could have production run on a different deployment of read agents, so that you get the blast radius isolation there, but still share the same underlying data set.
We have one person who I think they're going to do this next month. They have this kind of crazy use case that I think is really cool, which is they want to have a single logical Kafka cluster that spans multiple cloud accounts. And if you think about what you'd have to do to achieve that with like open source Kafka, like with like peering VPCs and punching holes through the, whatever. And they asked us how they could do it. And, we're basically like, just figure out how to share the S3 bucket across all 3 cloud accounts, and then everything else will just work.
It should just work. Yep.
Yeah. And I was like, yeah. So I think that's also a really cool thing you can do.
Wow. That's super cool. Okay. I want to do like a few just closing questions on, in this area on like the things that have changed or that like prompted this rethink and what you think about it. So you all are like big fans of object storage and just like how it's changing data systems. Is this like mostly an analytics revolution, or is this going to slip into like transactional workloads as well? Like I know we see like Neon out there sort of experimenting with this. Like, are we going to see object storage become a huge part of transactional workloads, or is it more, at least like not quite as latency sensitive stuff?
So the way that I like to think about object storage is it's just like an infinitely large array of hard drives. That's the way that you can think about it from a performance perspective. And large arrays of hard drives never had particularly great performance characteristics, especially if you ran workloads on them that had lots of IOPS, like they needed lots of IOPS. So we've always had this kind of slow storage, back to when you were running things in data centers. This kind of slow storage has always existed, and it's always been at every part of the hierarchy, from analytics workloads to operational workloads. It was always there. I think with the advent of SSDs, people have kind of forgotten how to make use of slow storage. But now that object storage is so important from a cost perspective, people are going to have to learn how to do it again. And it's going to have to become a part of operational workloads. Obviously, you have the storage hierarchy. So you have memory, you have disk of a bunch of different kinds, and then now you have object storage. It's even slower than an array of disks, but it's still in that same ballpark. I think it's going to naturally end up just through people redesigning storage systems. It's just going to end up at the bottom of the storage hierarchy for everything, not just analytics workloads. Because even within operational workloads, there are hot and cold sets of data, and you need access to it at some point in theory, and you can't just throw it all into some analytics system that makes it unusable most of the time. It still has to be available, either just because a user might keep clicking that back or the forward button until you get to page 50 on your application. It still needs to be there. Just they'll probably be okay if it took 50 milliseconds to read instead of 500 microseconds.
Yep. Very cool. Okay, another question I have. So a big benefit of WarpStream is reducing or removing cross-AZ networking costs. I've been trying to get to the bottom of this. Do you think cross-AZ networking costs, is that just like purely a racket? Does it like reflect at least like some sort of reality? Like what are your view on cross-AZ networking costs? Do you have any?
I think the sticker prices that are charged are probably a bit of a racket. Like I've seen the discounts I've seen be given to organizations that commit. Like I've met a number of people who have 90% plus discounts on those fees. I have never met someone who has like a 90% discount on S3 or EC2. So the margin's just obscene there. I do think though, to a certain degree, dude, I would love to spend some time with someone who actually designs data centers. I found some books on Amazon that I haven't read. I suspect that there's probably some, like, it's not too hard for, Amazon or GCP to add additional links between their availability zone buildings, even if they're like 30 miles apart, but it costs something. And like, it's preferable if they can encourage people to design their applications in a nice way. And even though S3 is like, multi-zone, right? It's not triply replicating. So they're way better at ensuring the data is available in multiple zones than, your triply replicated Kafka cluster is. And they probably also, that traffic's probably a lot more predictable. So I bet some of the pricing is designed to encourage good usage of the available resources, but the sticker prices are, they're crazy high. I don't know.
Yeah, I think it just reflects the fact that it's presented to the user as a limitless resource, whereas it's actually not. There are physical limits to it. And if you're an enterprise at serious scale, you're going to pursue a discount on that regardless if it's an important part of your workload. So it's just something that you have to, if you just have to notice that it's there, basically. That's it. If once you've noticed that it's there, you just have to make a commit to your cloud provider, and they'll probably give you something.
I like that answer. Yeah, I think y'all right. Like it's not like purely racket. Like they need to signal and communicate like that this is not a limitless resource, and have people find cost-effective workarounds like you all have done around this stuff. So I think it's a useful signal in that way. It's probably, it's expensive and things like that, but I think it's like not a pure rent-seeking racket like most. So
the part where I think it becomes very problematic is if you're a small team in a small company that needs to manage large company-shaped workloads. And so, but you don't yet have any leverage basically to negotiate with them, and you're kind of stuck with, and like, that doesn't sound like a common use case, but like if you're a startup doing literally anything in the data space, it's like really painful and you have no leverage, right? So.
Yeah, makes sense. Okay, I want to switch gears a little bit because I just think you both are interesting people and just like things I've learned from you or hot takes I've seen. So one thing I've seen, I guess like the standard advice is don't build your own database at a company, anything like always sort of use an existing one. But Richie, recently you were saying, that's the standard advice, but it's a little bit stale, like for different reasons. I guess maybe you want to expand on when does it make sense to build your own database, or what has changed to make building your own database feasible and reasonable?
I just think there's so many good primitives you can use today. I mean, like WarpStream is a great example with object storage. So is Husky at Datadog. Like, if you can just like, okay, I just don't have to think about data durability, data availability, data replication. I can focus on like data structures and application level semantics that make sense for whatever this like custom database I'm doing does. It's just like the barrier is so much lower than it used to be. I think it's like if there's still the thing I usually encourage people is like if you can find a way to not be programming a block device or a file system, there's still some use cases for doing that. Like obviously someone has to write that software, but if you're at a company and you're at that point, I would maybe think about what you're doing. But like if you're relying on primitives like RocksDB, object storage, DynamoDB, other storage systems to kind of handle the low-level nuts and bolts, and you're focusing on like, I have this use case and I can build data structures or access patterns or indexes that, give me an order of magnitude improvement over something more generic. I think that's where leverage is built. That's where, technical kind of competitive advantage is built. And I mean, it's just crazy what you can do today. I mean, our team is very small. Our company does not have that many people, but like, if you lean on good primitives like AWS and, their network load balancers and their object storage and some of their data stores, I mean, you can build mature battle-tested infrastructure that would have required, hundreds of people to build just 10 years ago.
Yeah, I think that really the focus needs to be on what is the differentiated value that you can provide by getting a couple of layers lower than just throwing all your data into a SQL database and running a query. If you can find that and you have a big enough business to justify the overhead for development, I don't think there's really any reason to avoid it anymore, because most of the serious concerns about writing your own database are around you're going to lose the data because you don't know what you're doing in terms of interacting with the file system. You're going to do something wrong from like a distributed systems correctness perspective and corrupt your data that way, which that one's another real concern. But when we're talking about building our own database, like when we made Husky at Datadog, we leveraged FoundationDB and object storage, and we still provided a very interesting and rich query interface for the data that we stored. The differentiated value was making sure that we could do it at a price point and at a certain scale that if all of the other potential solutions didn't make sense. So that's, we weren't concerned about losing the data because we were leveraging FoundationDB and object storage. And from a distributed systems perspective, things are a lot easier when you're relying on a database that has transactions under the hood. So it's just the definition of database is can be flexible enough to help you. Not everything is I'm going to rewrite MySQL. There's a lot of stuff on that spectrum there. And
Husky is a great example, I think, too, because like if you look at what Husky is essentially a columnar store built on top of object storage, and there's like kind of a lot of those now. There weren't as many when we started building Husky, but like you can imagine we could have just like used ClickHouse and used tiered storage and whatever. But like Datadog has a couple of constraints that most people building those systems don't have, which is that the data is completely schemaless. Like you can stick a UUID in your log key and just pump those out at 1 million per second at Datadog, and they'll bill you for it and it'll work. And making that work on a traditional columnar store where like they all have warnings that like don't put more than 10,000 columns in, or whatever. Whereas, Husky could support millions and millions of columns in a given data set. The fact that it can do type inference at query time, like if you go use the Datadog UI, you can emit fields as like a string, an integer, and a float with the same field name and query it and do math and get sensible results. And like trying to do that on existing columnar stores is also, so there was like a couple of other things. There's enough there that like to warrant, the overhead of building yourself. Also just all the multi-tenancy stuff, right? Most of the existing systems don't help you with that. But to Ryan's point, picking your primitives is like really important. Like if you pick those wrong, that can basically sink your entire project. And so those build versus buy decisions, it's not easy. It's really hard to get those right. And I don't know if it comes from anything but experience, but there's still a lot of stuff out there, I think, where there's plenty of room to improve. And
yeah, can you elaborate on the primitives? And I know you mentioned like build versus buy recently as well. I guess like what are some of those elements that you had to choose, like, you know, build versus buy on, and like, yeah, what did you? I mean, obviously, object storage sounds like FoundationDB for things. What other things did you consider, or elements of your system do you have?
For Husky or WarpStream or
so for I guess for either of them, like what are just like facets of this that you need to think about, and how did what choices did you end up making?
It's a good question. You want to talk about WarpStream?
Yeah, we can talk about WarpStream a little bit, but I think before we get there, there were some other good examples in Husky about like how we made the decision. Like one of the options for metadata was always just put it in Postgres.
Or Mongo.
Yeah, or Postgres or MongoDB. Like the Datadog, being a big company, has a proliferation of storage systems internally for lots of different reasons. And there were other options besides FoundationDB. Like FoundationDB wasn't an option when we showed up; we brought it. So that was the.
It was actually really controversial at the time.
Yeah, it was very controversial. But the problem with building something like this on Postgres is like, what's the multi-tenancy and scaling story? Like if you were shipping a product that's like Husky, but the customer is going to run it entirely themselves. Postgres may have been a very reasonable choice there because they could run their whole workload on one Postgres machine and then it's fine. But if you need to support thousands of tenants, then that's, it's going to be a very different story in terms of wanting to provide them a good isolation experience. What's the overhead of managing, a bazillion little Postgres clusters? That's one of the build versus buy decisions. Another one was on the file format side. Like we created our own file format instead of just using something off the shelf like Parquet for, there were a lot of different reasons, but like one of the very obvious ones is we had to build a full text search index, and Parquet is not a full text search index file format. And when you're building a full text search index, you need to understand the IO access patterns very well. So designing the format will help you do that. Because it runs on object storage, we can't just assume that there's an SSD to query a bazillion times to fill the index. And yeah, there's just a lot of little ones along the way. But I think that the cloud providers, if you're willing to accept a dependency on cloud provider services, you have a ton more options there as well. Especially with S3, that one's pretty obvious. No one's going to choose something else. But if we were, we had the choice to build versus buy on the database for WarpStream that we use internally in the control plane. And we wanted to give ourselves the flexibility to, in theory, ship a version of WarpStream that ran entirely within the customer's cloud account, like the control plane and the agent data plane. We didn't choose FoundationDB specifically for that reason, where we don't want to force them to have to take on the FoundationDB dependency, because it's easy enough to run, but it's still probably, a non-starter for somebody who's paying money for.
Well, it's just like there's like three companies that know how to do it. It's not hard, but
it's not hard, but you still have to, there's a little bit of a learning curve to it.
Yeah.
So in the end, we went with we chose a very limited interface of what we decided we needed. And it's something that's offered by every cloud provider, basically. So we chose a limited enough subset of what we needed out of a database in our control plane so that we can ship it on every major cloud provider without having to make major changes to our application. So that was an example where we decided to, buy a different product, but basically, an open source product is closer to using an open source project is closer to building than it is to buying sometimes. So it's that's why we went with buying this time.
Yep. What are your two history with FoundationDB? And it's one of those things that like certain people just rave about and love, and then just like it's not as widely known because it's very specific use cases. But I think a lot of like systems people just love it. So
there's no corporate sponsor. I think that's the main reason it's not widely known, to be honest. But
yeah. I mean, like, had you used it before Husky? Like, what was your sort of background, or how did you get into Foundation?
So when it was open sourced, I just got extremely interested in it from like a technical perspective. There was I didn't have any history with it prior to that. It's very useful for learning about distributed systems just because it's kind of weird in the way that it's designed. It's
extremely unique.
There's a lot of
actually, it's a good example of making one trade-off that other people are not willing to make or don't think is right, and then having massive simplification fall out of it.
What's that trade-off that they make?
The trade-off with FoundationDB is that what's it called? The recoveries? Is that just what it's called?
Yeah.
That's the trade-off they make.
Yeah, if any one of the nodes in what they call the transaction subsystem fails, which is like a subset of your
cluster.
Your cluster. Like if you're running a large cluster, maybe it would be 10%, 20% of the nodes. If any one of those nodes fails, all of the writes to the cluster stop. Like you can't process any transactions until they replace that node by reconfiguring the cluster. And the reconfiguration happens, on the order of 1 to 3 seconds for a not particularly large cluster. But during that time, the cluster is down. But because of that, so many other great things fell out of making that choice. And most applications can tolerate that, especially because the client bindings have a built-in retry loop that if you hit that error code while your transaction's running, it will just restart it. Like would happen if you had a conflict when your transaction was committed. It's the same idea, basically. So most applications don't notice anything other than a small latency increase for that second. But
it drives people crazy. Like you explain that to like distributed systems people, and they're like, you can't do this. And it's like, but they did, and actually it works great, and it's like way more reliable than most systems built the other way.
Yeah.
Because what they can do is just like for a bunch of the roles in the cluster, they're just like, it's this node, and this one's this one, and this one's this one. And if it fails, we'll just go through a recovery. Like all the error handling is just like do a recovery. And so they just made that really fast, and they test that a lot. And you end up with this like really, really efficient system. But like that's not a trade-off that most systems would die. Like someone would propose that and they'd be like, no. And so you'd have to go through some other much more complicated architecture. But they were just like, no, we think this is the right trade-off. And they got, I think, like I've operated Cassandra, Elasticsearch, MongoDB, etcd, Zookeeper. What are the other ones?
MySQL, Postgres.
MySQL, anything you can name, I've been on call for it at some point. There is just nothing that even remotely comes close to like Foundation. It just like never lets you down. It just will always do the sensible thing. It tries really hard to never lose your data. We had so many scenarios where we like realized we'd been doing something wrong, and it was just like fine because like FoundationDB was just like really quickly fixing it under the hood. It's just like hard to explain that there's just very few systems that you ever use that are just like that thoughtfully designed and work the way they're advertised, and FoundationDB is like the only one I can think of.
Would it make sense for a cloud provider to offer a FoundationDB primitive, like a managed version, or does it sort of not work because it's like, I don't know, so low level or something like that?
I think that the main problem with somebody offering FoundationDB directly is the fact that the client bindings are a C library that speaks essentially like write C structs over the wire protocol. It's doable with a lot of work, I would say, but overall, just like the segmentation of the networks would be a little funny. You'd have to build your own proxy that would cause a bunch of reliability problems, I imagine. But there's nothing stopping anybody from offering somebody that is like all of the interface of FoundationDB over a different protocol. Like you could build a protobuf interface that you could stick in front of a load balancer and maybe lose a little bit of the efficiency, but you could still totally offer that. The other thing that I think is a little weird about it is FoundationDB has limits in the sense that it's not a completely horizontal, like it doesn't perfectly horizontally scale forever to unlimited size databases. and it's not very friendly to the type of it would be very friendly to the type of automation that like you would imagine is behind DynamoDB, where there's like an absolutely massive fleet of machines that run shards that are kind of self-contained. Like it doesn't work that way. So you'd have to build a lot of really good automation around increasing and decreasing the size of individual clusters. And that's tricky. Getting the quality of service right on that is also, I'm sure, really tricky if you're going to try to do it in a multi-tenant way. But I would love if someone did. That would be cool. But it's definitely a big engineering challenge. And I imagine anybody that gets close to that, they would probably want to start from scratch and just build a new system that had the same semantics instead of using FoundationDB directly.
Are there any other primitives that you wish existed that you ended up having to build yourself for whatever reason?
I think S3 Express One Zone might fill a little bit of this role, but occasionally having a scalable, relatively low latency key value store for large chunks of data, we may have decided to change the way that Husky worked if, the pricing of S3 Express One Zone may not have made this practical, but in Husky, the query nodes had local disk caches, and there may have perhaps been a way to build a cache that would allow you to query it from multiple nodes instead of just whatever was on the local disk of one of the query nodes, or like tiering for the cache. That I think S3 Express One Zone will definitely fill a big hole in like people building caches for their systems.
I have another one that's in that vein. Well, it's related to caching maybe, but different, which is it's more of a library thing than it is like a cloud primitive or whatever. But like, I feel like external caches get really overused. Like in all the systems we've built, including in WarpStream and the control plane and the agents and stuff, we lean pretty heavily on just like having caches in the application itself, and not like, as soon as you have to introduce a Redis or a memcache or something, it's just this other piece of infrastructure, and like it's just remote memory. Like, why do you need to manage separate machines for that? And I think better primitives around essentially, I want all cache loads for this type of key to go over here, and I want to be able to essentially introducing data locality into an existing application. Actor frameworks are one way to express this. Elixir and Erlang's kind of OTP framework is another way to express this, basically making it easier for people to do more distributed systems things in their application in a sane way. I feel like we always end up kind of making stuff like that for ourselves because we're just like, I don't want to manage all these external dependencies, and I want to have, you get to pick one or two dependencies and then everything else has to happen in the application. Like that's how we usually build things. And that usually requires writing kind of these like, these libraries to do stuff within the application. And I feel like if more people had access to those things and there was better toolkits for that, but it's really tough to figure out the right programming model and the right interfaces and stuff like that. But
yeah. That's super interesting. Going back to that S3 Express One Zone, if you could sort of change one thing about it in a year or two, would it be the storage cost isn't as much? Would it be it's actually in two zones, right? So you don't have to worry about a zone going down. Would it be I can't remember what I had. I had a third one, but like what would you change about S3 Express One Zone that would make it even more helpful to you?
I think the biggest one would be to remove the bandwidth pricing that's kind of baked in after you write half a megabyte.
That was my third one. Like the 512. Yeah. Okay.
Yep. So I would love for that to go away. I understand why. It's there.
Why is it there?
Basically, you could use it to do the same thing. Like the way that WarpStream works is, ideally you have as few puts as possible, but you make all of those puts as large as possible, because you're not billed based on the volume, you're based on the number of puts. So, we try to use multi-part uploads, and
This is to avoid the interzone networking
Yeah.
and also keep the put cost low. But
yeah. So you avoid interzone networking by using S3 standard. You make as large of puts and gets as possible. Puts are more expensive. And if you could use S3 Express One Zone in the same way that you can use S3 standard, where you write as much data as you want and only pay for one put, that would be great for us in the sense it would make everything way cheap. It would just be faster and cheaper. There would be no trade-offs other than like the very slightly increased storage cost. But what we would do is we would just write it into S3 Express One Zone and then use compaction to move it to S3 standard. So we would only pay for the increased price for a relatively short period of time on the storage side. So I understand exactly why they did it. They don't want you to use S3 Express One Zone as like a way to do cheaper cross AZ bandwidth, and they don't want you to use it in the same way you use S3 standard, where you can use drastically more. Like, it's more expensive to write data to what are presumably SSDs. So they have a limited lifetime. You need to pay a little bit for the I/O that you do, whereas hard drives are that you can rewrite them as many times as you need. So I understand why they did it, but that would be the one thing that I would change about it.
That's very good.
The replication is annoying in the sense that we have to build something in order to add replication to S3 Express, but it's not the end of the world. That one is definitely solvable.
I just realized something too that I think is another interesting thing about the difference between manually replicating your data and having S3 replicate it for you. Besides just like, it's better because it uses erasure encoding and they can have dedicated links and stuff, which is also that when you manually replicate your data, whether it's with single zone, S3 Express, or just in your application, the AWS has no control over which essentially data centers or availability zones that data gets replicated to. Whereas with S3, they actually get to choose because it's not exposed in the interface. Right, so you can imagine if like one of the availability zones is slightly degraded or under capacity, they can essentially traffic shape. Whereas if you're doing it yourself, they don't get that control either. So I think that might be another interesting kind of data center design question.
Very cool. Cool. All right, I want to wrap up with just like a few questions around business stuff and WarpStream, as a company. So I guess like first one, like, what's your billing model? How will people use WarpStream? Is it fully hosted service? Is it sort of run your own? Like, what's it look like there?
Yeah, we have one product offering right now, and we're about to release the second one. So the product offering we have right now, we call it BYOC. We've been debating the name a little bit internally, whether we should call it self-hosted or whatever. But the idea is WarpStream is designed with a data plane control plane split. And so the idea with the BYOC product is the data plane runs in your cloud account, and the control plane runs in ours. So there's essentially no networking fees between the two cloud accounts, except for metadata, which is super small, on the order of tens to hundreds of kilobytes per second. And also you get all these nice privacy and security benefits because the data literally, doesn't leave your cloud account. We call that BYOC. We're still kind of going back and forth on the pricing for that. I think most likely what it's going to end up being is just usage-based pricing on 2 dimensions, but just with like a much, if you imagine this is the slope of the cost for self-hosted open source Kafka, WarpStream cloud cost plus, our licensing fee will look like this. It'll just be a much less steep slope. And we'll only price on 2 dimensions. It'll just be on write throughput and storage pricing, most likely. So however much data you're retaining, plus however much data you're writing. We don't think we'll bill for like agents or cores or reads or anything for that product. But we'll see. And then, for larger use cases, there's probably some options there for around like fixed size pricing and stuff like that for people who want more predictability. We're going to, launch our serverless product probably mid next quarter. That's like the same exact technology as WarpStream, but essentially the data plane also runs in our cloud account, but it's run in such a way that it's fully virtualized, kind of scaled to 0. You can go from like 0 megabytes per second to 100 almost instantaneously and back down. That one will unfortunately just have to have more dimensions to the pricing because it's just like there's a lot of different ways you can incur costs for us. And so we're still figuring out. There'll be more dimensions to it. Reads will obviously cost something because there's egress fees, and some of that can be mitigated with private link and stuff like that. But that one will have more dimensions. But under the hood, it's leveraging the same WarpStream technology. So what you'll get though is, a lot of the other people kind of selling kind of hosted Kafka, it's not super obvious in the pricing, but eventually they make you pick, like, is all your data in one zone, or are you willing to pay extra to have it in multiple availability zones? And so with the WarpStream serverless product, you'll get, essentially usage-based pricing, scale to zero. Everything will always be not triply replicated, but stored in S3, so multiple availability zone storage. And it'll be a lot cheaper than, anything else out there.
Yep. Yeah, that's pretty fascinating. I think especially like scale to zero and just being able to quickly sort of scale up to whatever you need to. That'll be pretty interesting. And another question I like to ask people, especially that are building like data products like this, is how do you work to convince people of its reliability, right? How do you have people put their trust in like, hey, this is a new product that's holding my most important data or something like that? Like, what's that process sort of look like, and how do you get them onboarded onto it?
Yeah, so I think it starts with we wrote a bunch of blog posts in the beginning that explained bits and pieces about how the technology works. And I hope that shows people that we know what we're doing from a technical perspective. Like, the information is dense and interesting. To give, slightly more of an explanation about what we do internally, we have a pretty serious set of correctness tests and integration tests for our system to ensure compatibility with a bunch of the client libraries, and we take the durability. Obviously, the data is in S3, so that's the data plane data is all in S3, but the control plane data is also stored in S3. And if you're in Amazon, and if you're in Amazon, also the control plane state is stored in DynamoDB. Some of it, and we take backups of that information. Depends on how often, depends on how much you write to the cluster, but we take backups of the control plane state many times an hour if you're on a high throughput cluster.
We do a lot of fault tolerance and fuzzing and stuff like that too. We have a bunch of integration tests that essentially we run I forget what the term is, but we have another implementation on the side that's tracking what the outcome of every produce and fetch should be. And then we inject faults all over the stack, up to pretty high ratios, and make sure that everything that was acknowledged on the right side comes out on the other side in the right order, uncorrupted. So we do a lot of aggressive testing, like that as well. It's not fully determinized, in the same way that Tiger Beetle is. But we do a ton of fault injection. And we do a bunch of other crazy stuff. All our staging clusters run basically at 95% CPU all the time, and have really obnoxious workloads with really poorly tuned clients to just stress test the system.
Randomly delete topics every 10 minutes.
Yeah.
So that nothing explodes.
Yeah. So a bunch of stuff like that. I think a lot of that trust also just comes with time. As we spend more time developing the system, as more people adopt it, as more people see the value. But it's hard. I think it's not as hard as selling a new database that's stores data forever, but it's close to how that hard, because if you just think about how critical Kafka is in a lot of people's workloads. So I think it comes with trust and time. Yeah.
But we do have one user in production that's been with us for a while now, and their usage has been growing, and they're very happy with it. We'll probably do a case study with them relatively soon, but we have people that are using it in production and doing proof of concepts right now, and they're finding many fewer bugs than they did 6 months ago. Now we've ironed a lot of things out. Mostly the bugs are around you don't support this thing, or you support it in the wrong way that doesn't look exactly like open source Kafka does. They're not really, they weren't really correct issues. They were just, the protocol is huge. So we're making a lot of progress there. For most simple usage of Kafka, you can just point your existing clients at it, and it will work today.
Yep. Yep. Very cool. And I think that's just the process for like a lot of, data systems, where it's like you got to get some clients where they have enough pain either from the costs or the operational issues. And they're just like, hey, we got to make something happen. And you build up enough of those and get the case studies and get the word out there like that this is working, and it just builds momentum on itself. So it's fun. It's a fun time to see like the Kafka space because, Confluent, like, the big gorilla in the room or whatever, but then you all like squeezing them from the cost side and operational side, and Red Panda squeezing them from like the latency performance side. Like it's a fun time to see what's happening in this space.
Yeah, I think the streaming space is going to look really different 10 years from now. We're pretty excited about it.
Yep, absolutely. Richie, Ryan, thanks for coming on. I learned a ton. This is really fascinating stuff, and I appreciate you like getting down in the weeds with me for all this stuff. If people want to find out more about you or WarpStream, where should I send them?
You can go to our website at warpstream.com, and then we have I think the Twitter account's called WarpStream Labs.
Yeah.
And we have a LinkedIn now too. But the website. Oh, and also the place we're most active, if you want to just come talk to us directly, is our community Slack channel. And there's a link to that on the website.
Perfect. We'll get those on the show notes. I'm going to link in some of your blog posts as well, because like I found them really fascinating and useful. So I think other people will as well. But yeah, thanks again for coming on. Best of luck to y'all at WarpStream going forward.
Cool. Thank you so much for having us.
Thanks.